Okay, we'll be continuing on the discussion on work and electric potential energy. So we'll have the sample problem now. Okay, so a point charge Q sub 1 is 2.4 microcoulombs is held stationary at the origin. A second point charge Q sub 2 is negative 4.5 microcoulombs moves from point with the coordinates x 0.150 m, y is equal to 0, to the point 0.250 meters, y 0.250 meters. So how much work is done by the electric force on Q sub 2? Okay, so perhaps it is quite difficult to visualize what is happening here. So I suggest that what you do is you try to draw the given problem in a piece of sheet of paper. So as presented in the problem, this is the same problem that was presented in the PowerPoint presentation. Q sub 1 is actually located at the origin. So if you're going to draw Q sub 1 at the origin, uh, a second point charge which started to move from point A, which has the coordinates x 150.150 meters, y is equal to 0. So that means point A is actually at is on the x-axis. Now, the second point, which is point B, a designated point B, is at the has the coordinates x is equal to 250 meters, y is 250 meters as well. So that means both of these two distances are designated positively. So that means if you're going to draw this, this should appear, point B should appear on the first quadrant. Okay, so our Q sub 2 moves from this point on the x-axis and moves towards point B on the first quadrant. So the question now is how much work is done by the electric force on Q sub 2. Okay, so before we proceed with the computation for the work, okay, so first we take note of the distances since we're going to need the values of the distances from of Q sub 1 from of Q sub 2 from Q sub 1 in the designated locations point A and point B. Okay, so let's start with point A. Of course, since Q sub 1 is on the origin or is at the origin, and Q sub 2 at point A is in the location which is on the x-axis, so therefore the distance between Q sub 1 and Q sub 2 at that point is equal to 0.150 meters. So R sub A would serve as equal to 0.150 meters. Now as for point B, point B is the location of Q sub 2 at the second location, point B. Now the distance of Q sub 1 from Q sub 2 from Q sub 1 at the second location is simply found by getting the hypotenuse of the triangle formed by the distance x 0.250 and y 0.250. Now, of course, since 0.250 meters and y 0.250 meters forms a square, so therefore the diagonal of the square is simply the square root of 0.250 meters square plus 0.250 meters square. You get the sum, then you get the square root. So simply you would arrive with the same value, which is 0.250 meters. So try to verify also what did we arrive with such computation. So if we're going to verify this, that would be square root of 0.250 meters square plus 0.250 meters square. So you get the sum of that, then you get the square root. That should be equal to 0.3. This should be 0.354 if you're going to round that off to the nearest third decimal place. So that would be 0.354 meters. Okay, so how did we get the value again for 0.354? 0.35 meters, we make use of the Pythagorean theorem in order to compute for the diagonal of the square. Since the coordinates 0.250 and y 0.250 forms a square, then the diagonal would be the hypotenuse of one of the triangles, with forming your square, then using Pythagorean theorem to solve for that hypotenuse or the diagonal of the square. Okay, so again, that is square root of 0.250 square plus 0.250 square. Okay, so let's proceed now with the next step, computing for the work done. So in order to compute for the work done, recall that in order to get the work done, by definition, work is equal to the negative change in potential. So that is equal to negative U sub B minus U sub A. So if we're going to distribute the value at the negative sign, so that would change the position of U sub A and U sub B, so that becomes U sub A minus U sub B. And substituting the formula for U that we have presented in the first video lecture, remember that U is equal to Q sub O over R. So for U sub A, that would be Q sub 1 Q sub 2 over R sub A. Now for U sub B, that would be Q sub 1 Q sub 2 over R sub B. Okay, so try to notice to simplify the expression further. Try to notice that we have the common terms KQ1 and Q2, so we could actually factor out KQ1 and Q2 outside of the grouping. So what is left within the grouping is 1 over R sub A minus 1 over R sub B. Okay, so next step in the computation is the substitution of the value. So we have 9 exp9 for K. Next is Q sub 1, which is 2.4 exponent negative 6. Negative 6 comes from the prefix micro. The prefix micro refers to 10 to the negative 6 coulomb in terms of degrees of magnitude. Okay, so 2.4 to the negative 6 coulombs. Multiply that with 4.5 microcoulombs, so still that is 10 to the negative 6. Multiply that with the combined value of 1 divided by 0.150 meters minus 1 divided by 0.354 meters. Okay, so in your calculators, you should be able to verify this in your own calculators. Remember the syntax for inputting the values in your calculators. This is considered as a single term, so you could first compute for 1 over 0.1.5. You could compute for 1.354 individually, then you get the difference. The result of this, you multiply that with the corresponding terms that appears in your product. So expectedly, this you should be able to get the value 0.373 joules of work done. Okay, so the point here is for you to compute for the work done, instead of making use of the form of the work done, that which is equal to force times the distance between the displacement covered by the object. So we have the approach of computing for the work done, making use of the computation of the electric potential. So now, of course, what the result here is that the result for the work done is negative. So indicating that if the work done is negative, the associated value for the electric potential energy is that the electric potential energy increases. Okay, so next in our topic discussion would be electric potential energy and with several point charges. Okay, so what we have presented in the first video lecture is that we have the form of the electric potential energy U, which is equal to Q sub O over R. Now, this form of the equation of the electric potential energy is computed in for a system of charges, particularly for two charges. So you have Q sub O over R. Now, if you have an assemblage of charges, meaning you have two or more charges, then the question is, how do we compute for the total electric potential energy of the assembly of those charges? Okay, so for example, in our illustration here, you have Q1, you have Q2, you have Q3, and you have Q sub O, which is our test charge, and you have Q sub 1 to Q sub 3 as your source charges. So the question now is, if you're going to place Q sub O at at this particular location, what, of course, individually or pairwise, Q sub O forms a pair which has its own potential energy. The same goes with the pair Q sub O, Q sub 2, Q sub 3, Q sub O. Then it follows you have this assemblage of charges would actually have individual values of the individual pairwise values for the electric potential energy. So the question now is, how do we compute for the total electric potential energy? So as what you see here, simply what we can do is to compute individually for the associated potential energy on Q sub O with respect to the individual source charges Q sub 1, Q sub 2, and Q sub 3. After which we can actually add them together after computing for the individual values. So simply, the total would come from the sum of the computed pairwise values of the form Q sub O over R. So let's try to make work of the formula. So consider this problem. Okay, so the problem that appears in the PowerPoint is the same problem that appears here. So 2-point charges are located on the x-axis, Q sub 1, which is negative E. Remember, negative E is the charge of the electron. So the charge of the electron is negative 1.6 to the negative 19 coulombs. And it is located at x equals 0. Q sub 2, on the other hand, is has the charge positive E, or a proton, located at a distance a from the origin. So the question is, find the work done that must be done by an external force to bring a third point charge Q sub 3, which is positive E, from infinity to x is equal to twice a. And letter B, find the total potential energy of the system of the three charges. Okay, so recall that the work done has the form F times D, or force times the displacement, and the force is given by Coulomb's law. So F is equal to Q sub O over R square. Of course, D and R are the same, so we have work is equal to Q sub O over R square times R. One of the R's would cancel out. Therefore, we arrive with the form of the work done, which is equal to U is equal to Q sub O over R. Note that the sign of the work indicates whether the system of charges gains or loses potential energy when in assemblage, or when they are put together. Okay, so pairwise we have the electric potential energy between 1 and 3, so that is KQ1 Q3 over 2A. Between 1 and 3, the distance is 2A. Okay, so that is K is equal to negative E over 2A. Take note that when we compute for the electric potential energy, if the charge is negative, we substitute it as negative. If the charge is positive, then we put it in the solution as positive. Okay, so we have K negative E over 2A, so that is negative K E square over 2A. Now for the pairwise Q sub 2 and Q sub 3, of course Q sub 2, Q sub 3 has the distance A in between them, so the electric potential energy associated between 2 and 3 is k q sub 2 q sub 3 over a. That is k e times e over 2 over a. So that means you have k e squared over a. Now, so the question now is find the work done that must be uh, done by an external force to bring a third point charge q sub 3 from infinity to the position of x sub 2 to a. Okay, so next step in our solution is to compute for the third pairwise, which is between 1 and the total work done would come from the sum of the uh, effects of the two charges present, q sub 1, q sub 2, on q sub 3. So that is uh, u sub 1 plus u sub 3. Wait, u sub 1 3 plus u sub 2 3. Notice that we need not to compute for the other pairwise between 1 and 2, since we are only asked to get the total work done of the two present source charges q1 and q2 on the third charge q3. We are not asked to get the additional effect between q1 and q2 themselves. So it is which means our solution is only limited to between 1 and 3 and 2 and 3. So therefore, if we're going to compute for the total potential energy, the total potential energy would come from the sum of u sub 1 3 and u sub 2 3. So since u sub 1 3 is equal to negative that is negative k e squared over 2a, and q sub 2 3 is equal to k e squared over a. So therefore, we simply add these two terms. We should be getting the form E is equal to okay, so k, this would be k e squared plus 2 e squared over 2a. Okay, so what I'm doing here is simply I'm simply adding the fractions together. So you have the two fractions with with two different denominators. One is 2a and the other one is a. So getting the common denominator between 2a and a, that would be 2a. 2a divided by 2a is 1. 1 times negative e. This is negative e. So that gives you negative e squared plus 2a divided by a gives you 2 times e squared, that gives you 2e squared. Now the common term k here, what was done here is that the common term k was factored out, so we can see that k here is outside of the grouping. So next step is actually getting the difference, simplifying the numerator, so that would be 2e squared minus 1e squared, so that gives you positive e squared. So 2 minus 1 gives you 1e squared over 2a. So therefore, what is left in our solution is that we have u is equal to k e squared over 2a, which is positive. Okay, now since from our definition of the work and the potential energy, since work is equal to potential energy, therefore work is simply equal also to k equal to E squared over 2A. So basically this is also equal to the work done. So what we have done here is that we have already answered uh, both letter A and letter B using one solution only. Okay, so just like what was mentioned from the first video lecture, we have already defined the idea of the electric potential. Okay, so the electric potential is the potential energy or work on a per unit charge basis. Our analogy that we have done here is just like what we have done in defining the value or getting the strength of the electric field. The only difference is that the electric field is the force per unit charge. It is a measure of a force per unit charge basis, whereas the electric potential is a measure of energy per unit charge basis. So force over charge against energy over charge. So force over charge is a measure of the electric field, while the um, energy overcharge is a measure of the electric potential. Or simply, to shorten the term, we simply call the electric potential as potential, just to differentiate it or not to confuse it with the electric potential energy. Remember that they are using different symbols. One for electric potential energy, we make use of U, and for electric potential or simply potential, we make use of the symbol letter V. The idea of the electric potential is useful in calculating energies of charged particles. And this is denoted by V, and the units for the electric potential is volts, just like the idea of the units for voltage, which is volts. So this topic in physics is the one that compounds on the idea of using the voltage in basic electronics. Okay, so our symbol for V is U over Q sub O, since the idea is that the electric potential V is a measure of energy over charge. Of course, in terms of units, one based on this association of our definition, we have the units for V as the volt, and which is equal to the unit of energy over charge, which is joule over coulomb. 1 joule over coulomb is equal to 1 volt. Okay, so I have presented already to you this form of the equation. So that means the work done is over Q sub O is actually the potential difference B sub A minus B sub B. Now, just like what we have done with the assembly of charges, getting the total electric potential energy of a system of charges, an assembly of charges, we can also do the same technique in getting the total electric potential or potential of an assemblage of charges. So by simply getting the sum of the form of KQ over R. Now, to illustrate what is meant by the previous form of the equation, let's have the final problem that is presented here in this module. Okay. Okay, so last problem we are given, this is the same problem that is presented in the PowerPoint. Again, in the given figure, we are asked to find B sub A minus B sub B, or the difference in the electric potential. So we are given the assembly of charge. We have positive 3 nanocoulombs. Nanocoulombs is 10 to the negative 9. And we have negative 3 nanocoulombs. And we have point A and point B, which has the following dimensions of distances from each of the given charges. So what is asked is, we are asked to find B sub A minus B sub B. Okay, so individually, we could solve for the values B sub A and B sub B, coming from the contributing potentials of both the positive 3 nanocoulombs and the negative 3 nanocoulombs at point A, and again for point B. Now recall in our discussion that V is equal to U over Q sub O, and also recall that U, as we have defined earlier, is equal to KQ Q sub O over R. Now, substituting the form of U in our definition of the electric potential, we have KQ Q sub O over R over Q sub O. Now, since we have a common term Q sub O, this cancels out. What is left in our form of the equation for the electric potential is that we are left with KQ over R. Notice that between Q sub O, Q is the source charge and Q sub O is the test charge. And this form of the equation, V is equal to KQ over R, enables us to compute for the individual electric potential for as long as we are given the source charge and the distance from which we want to compute for the electric potential. So we have V is equal to KQ over R. Now, that means individually we could compute for V sub 1A and V sub 2A, meaning the electric potential of Q sub 1 at A and the electric potential of Q sub 2 at A, then get the sum so that we could get the overall V sub A, or the electric potential at A. Okay, so individually we have KQ sub 1 over R sub 1A plus Q sub 2 over R sub 1A. What you see here is that I have factored out K as the common term. What is left in the terms within the parentheses is Q sub 1 over R sub 1A plus Q sub 2 over R sub 2A. Now, for the substitution of values, we have K is 9 times 10 to the 9 Newton meter square per coulomb square. Q sub 1 is positive 3 nanocoulombs, so that is 3 to the negative 9 coulombs. The distance between Q sub 1 and point A is 1 centimeters, so that is 0.01 meters. Now for Q sub 2 is negative 3 nanocoulombs, so this is negative, so we substitute the negative sign in our substitution. So negative 3 times 10 to the negative 9, the distance of Q sub 2 Q sub 2 from point A is 2 centimeters, so that is 0.02 meters. Now, you should be able to verify this in your own calculator, so you do the computation. Expectedly, you should arrive with a value 1350 volts. Okay, next, the electric potential at point B. So again, the electric potential at point B would come from the individual contributions of the electric potential from 1 and from 2. Okay, so KQ sub 1 over R sub 1B, KQ sub 2 over R sub 2B. Then make the necessary substitutions. Still, this is 3 to the negative 9 coulombs minus 3 to the negative 9 coulombs. But this time, in terms of the distances, Q sub 1 is 2 centimeters away at point B. Q sub 2, on the other hand, is 1 centimeter from point B. So that means this is 0.02, this is 0.01. So by result, this should give you negative 1350 volts. Now, last part of the solution is to get the difference between V sub A minus V sub B. Now, V sub A is given as 1350 positive minus V sub B. V sub B is negative, so negative negative gives you positive. So that means 1350 plus 1350 gives you 2700 volts. Okay, so this is the end of our topic discussion. I will be sending you a problem set regarding the topic coverage on Coulomb's law, work, electric potential, and electric potential energy, and I expect everyone to submit this on Friday. Friday would be on April 29. I'll be sending you the problem set tomorrow afternoon.